Hello students, today I am going to start chemical bonding. In chemical bonding, first of all, the first question is why atoms participate in chemical reactions? That means why elements participate in chemical reaction. Elements participating in chemical reaction means they are forming chemical bonds. So what is the main reason for that? The reason for participating in chemical reaction and forming chemical bond is to get stability. That is the reason. Already stable species do not do these things. Okay. So the first concept is the thing, but Lewis concept that is also called causal independently. These two scientists independently worked and came to same conclusion. They observed the noble gas elements. They observed the noble gas elements events. For example, you take helium, it is having 1s2 configuration, completely filled shell. First main shell is completely filled. Neon gas events, first and second main shells are completely filled. That means 1s2, 2s2, 2p6. Like that, helium is having 2 electrons in outermost shell. Neon is having 8 electrons in its outermost shell, 2s2, 2p6. Argon is having 3s2, 3p6, 8 electrons outermost. Krypton is having 4s2, 4p6, again 8 electrons in outermost. Xenon is having 5s2, 5p6, 8 electrons. Radon is having 6s2, 6p6, 8 electrons. So the presence of 8 electrons thought to be stable electronic configuration. So why Lewis and Coasel came to that conclusion? At their time, that means 1916, Lewis proposed this one. Lewis, extraordinary chemistry teacher now. Extraordinary chemistry teacher. Teacher is the general word. So different fellow, professor, and different post will be there. Okay. So I'm just telling about the general extraordinary teacher. And I definitely, my memory is correct. 23 students of his. That means he only started a chemistry department in America. Chemistry education in America. Lewis started chemistry education in America. Linus Pauling, two-time Nobel Prize winner, student of Lewis. 23 students of Lewis got Nobel Prizes. So you can imagine how good as a teacher Lewis. Okay, 23 students, if my memory is correct. Okay, but Lewis didn't get Nobel Prize. Lewis didn't get Nobel Prize. Okay, that is a sad story. I don't feel that means Lewis felt at that time not getting the Nobel Prize. And also most of the students are getting the Nobel Prizes at that time. Lewis felt bad about that. And I don't want to say on the record that means Lewis definitely felt really bad about that. But in my opinion, Lewis not getting Nobel Prize is bad for Nobel Prize, not the bad for Lewis. That was a great scientist, greatness of Lewis. Really, Nobel Prize missed the Lewis. Okay, so very really bad for Nobel Prize. I feel that way. So I adore Lewis now. Okay. So Lewis concept is very simple. Actually, really simple. We explained chemical bonding in the simplest possible way. Okay. Of course, Coastal also worked in similarly, but independently. I am not degrading Coastal, but Lewis was very popular at the time. So he observed the noble gas elements. Having the 8 electrons in outermost shell is nothing but called octet. Having the 2 electrons in outermost shell, helium, duplet, that is nothing but called duplet, duplet. Okay. A duplet means having 2 electrons in outermost shell. Octet is nothing but having 8 electrons in outermost shell. So noble gas elements, they do not participate in chemical reactions. They don't form chemical bonds. Okay. Later on, we saw that xenon is doing some chemical reactions, but at that time, they observed like that. So they felt that definitely noble gases are not participating in chemical reactions. It means having 8 electrons in outermost shell. That means having octet electronic configuration in outermost shell definitely gives a lot of stability to the atoms, the elements. So any other element, that means the sodium is there, it participates in chemical reaction. Fluorine participates in chemical reaction. Most of the all other elements participate in chemical reaction. And Louis told us any other element except noble gases participate in chemical reaction to get stability by getting octet electronic configuration. By getting what is the aim? For example, sodium is there. This is Louis' concept now. What really happens, I'm not at all telling. Okay. Louis' proposal, I'm telling to you. If sodium is there, sodium participate in chemical reaction, form chemical bonds, and during that process, it gets stability by getting 8 electron in its valence shell, outer portion, octet electronic configuration. Chlorine is there, participate in chemical reaction, form chemical bonds, and during this procedure, it also get 8 electrons in outermost shell, octet electronic configuration. So getting octet electronic configuration is the motto, is the reason, is the responsible for the chemical reactivity and formation of chemical bond. So that is the first thing here. So I start with the chemical bond. That means so this is the simplest possible theory. That's why I don't want to confuse you with the more sophisticated theories straight away. So I'm starting with the Lewis theory. Simple words. The electrons occupying outermost shell. You know already this is valency electrons. Lewis electron dot symbols. That means he proposed one easy understanding symbol. That is called electron dot symbol. That means electrons, valence electrons only. We don't bother about the core electrons. Core electrons do not participate in chemical bonding. Only valence electrons participate in chemical bonding. So the valency electrons are shown as a dots around the element symbol. That is nothing but called Lewis dot symbol. Show valence electrons as dots. I will give that one. Just simple words first of all. You go through simple words. Yes. Now here I clearly explained what I already did. Noble gases with 8 electrons in their outermost shells are stable and do not participate in chemical bonding. That is the inert. So noble gas elements with 8 electrons in outermost shells are inert. Having 8 electrons in outermost shell is nothing but called octet. But here within the brackets I given here, He means helium. Not this is helium. Now I'm not talking about English he. Okay, if I write he, that means English. She and he are there. So don't confuse. Okay, helium is having 2 electrons in its shell. It is called duplet and also stable. So helium also not participating. Never participate in chemical reaction. It's already quite stable. Okay. Any other element participate in chemical reaction and form bonds to get octet configuration. So that is the motto, to participate in a chemical reaction and form chemical bond. Now, how they get octet? Now, that means here in the 5th point, I written something. Before going through that point, let me explain here. Okay, that means noble gases having the octet configuration, helium is having duplet configuration, and they are stable. They do not participate in chemical reaction. They do not form chemical bonds. Every other element trying to get octet configuration, trying to get stability, participate in chemical reaction and form chemical bonds. This is the Lewis theory. But how they lose, that means how they get octet configuration. Getting octet configuration, I'm telling now. So how they are going to do that? That is the next point. Yeah, for example, you take metals. Sodium is the metal. Lithium is the metal, alkali metals, alkali and earth metal, transition metals. And the F block elements also metal. So most of the elements of the periodic table are metals. How metals are going to get octet configuration? By losing electrons. Metals tend to lose electrons. That is the property of metal. Metal always, in metals, electrons are loosely bound. So always trying to lose electrons. Excess electrons, that means, for example, this is only for example, sodium is having 1s2, 2s2, 2p6 electronic configuration, 3s1. If your sodium loses this electron, it immediately gets octet configuration. It immediately gets neon electronic configuration. Getting neon electronic configuration is quite stable. So sodium is trying to get neon electronic configuration by losing electron. So that is one procedure. So atoms of metal are having a tendency to lose their electrons, valence electrons. And by losing electrons, they are trying to get octet stable electronic configuration. That is one point. But when metal atoms lose electrons, if I am losing electrons, sodium is losing electron, you already know. Sodium gets a positive charge. Sodium gets a positive charge, depends. Sodium is simply forming cation. That is cation. So metal atoms lose valency electrons to get octet configuration. During this process, they form cations. The same sentence, the fifth point are written the same thing. Now, what about the non-metals? Non-metals, that means atoms of non-metal elements, okay? Non-metallic atoms. They are tended to non-metal elements, they have high electron gain enthalpies, high electronegativities. They tend to accept electrons. They are having tendency to accept electrons. They are having tendency to accept electrons. Definitely, non-metal atoms. This is some of non-metal atoms. I'm not telling all the non-metals do the same way. Some of non-metal atoms accept electrons, take electrons to get a stable octet configuration. But during this process, I'm taking electron. For example, chlorine is taking electron, means it gets negative charge. Negatively charged ion is called ion. So some of non-metal atoms accept electron to get a stable electronic configuration. During this, they form anions. Okay, but some non-metal atoms, that means for metals, there is no other way. They have to lose electrons, valence electrons, to get a stable electronic configuration. But non-metals having two different possibilities. They either gain electrons to get stable electronic configuration and form anions, or they can share electrons. Sharing of electrons is also other possibility for non-metal atoms. Non-metal atoms. They can also share electrons to get a octet configuration. Now listen, this. That means it's not a big thing. Slowly, I will develop the subject. Okay. So, for example, metal atoms. You see, metal atoms losing electron to get the stable octet configuration, forming cation. Non-metal atom gaining electron to get the stable configuration, octet configuration, becoming anion. Now, once cation, anion are there, there is the electrostatic attraction between cation and anion. That electrostatic attraction between cation and anion is called ionic bond. So, losing of electron by metal atom, gaining of electron by non-metal atom leads to cation and anion, and they are pulled together by electrostatic force of attraction. That is nothing but called ionic bond. But sharing of electrons, other possibilities I told you, the non-metal atoms gain octet configuration. Non-metal atoms get octet configuration while gaining of electrons or by sharing of electrons also. So by sharing of electrons, you are not going to get ionic bond. By sharing of electron, the bond is going to form is known as covalent bond. Covalent bond. So straight away in the first 10 minutes itself, I introduced two important bonding concepts. Ionic bond and covalent bond. That's all now. The entire chapter consisting of ionic bond and covalent bond. Ionic bond formation is quite easy. You already know from the lower classes you are studying the ionic bond formation. It's not difficult. Only some energetics related to the ionic bond is difficult. That we will discuss in thermodynamics, lattice enthalpies. But covalent bond formation, sharing of electron pairs is the Lewis concept. His student Linus Pauling proposed another theory, valency bond theory. He also proposed another concept, hybridization. And now another concept is also there for the 11th and 12th class, to the level of the 11th and 12th class, that is known as molecular orbital theory, MO theory. Okay. So the discussion of the covalent bond takes a lot of time, and it is a very big topic. Okay. Let me complete the first ionic bond, easiest one. Okay. So the same sentence I written on here, that means the fifth sentence already you know. Atoms of metal tend to lose their valence electrons to have octet configuration. They form cations in this process. Atoms of some non-metals tend to gain electrons to get octet. In this process, they form anions. The electrostatic attraction between cation of metal and anion of non-metal is known as ionic bond. Atoms of some non-metal, that means atoms of some non-metal tend to share electrons to get octet and form covalent bonds between them. So as a Lewis overall concept, I am giving that part also. So right now I will discuss the formation of ionic bond. Then later I will come to the different examples of covalent bonds and entire things regarding the covalent bond. So far I given 8 points. So I am just discussing Lewis theory as points. Okay, so easy to write in notes. Easy to write in notes and also easy to study. Now in the 9th point I am giving, already you know this one, how cations will be formed, but I am giving some examples. So this is the point number 9. This is formation of cations. So how cations will be formed? I told you metal atoms are tend to lose electrons. I taken first example sodium. Here you see I written one symbol here. And this is nothing but called Lewis dot symbol. Lewis dot symbol. So that is nothing but called Lewis dot symbol. You see the valency electron, the 3s1. I'm writing like a dot here. And this is the symbol. I don't bother about these core electrons. If this electron is lost, it will get a stable neon electronic configuration octet configuration. Losing of one electron means it gets one positive charge octet, and if it loses this 3s electron, gets octet configuration. So here I explained in the first example how sodium plus is forming. This is straightforward, very easy, you already know that. But what I am giving additionally, this belongs to the group 1. Group 1 means that is alkali metal. What about all other alkali metals? Sodium is forming Na plus. Na plus is called unipositive ion. Unipositive ion. That means one positive charge is there. Similarly to Na plus, similar to sodium, all other metals of group 1 also forming similar kind of unipositive ions. Similar way, all group 1 alkali metals form unipositive ions. So this is important now. So ease of formation of cation, I discussed it there. Here I written Li plus, Na plus, K plus, Rp plus, cesium plus. Another one is also there, that is the francium. plus. I'm not taking that is radioactive element. Okay. Name of cation directly is the name of element. So no change. Lithium is the element name. Cation is also will have the same name. Cation also bears the same name. But down the group here, I written something here. Before seeing this one, I am telling down the group ease of formation of cation increases. Sodium plus is easily formed than lithium plus. K plus is easily formed than Na plus. Rb plus is easily formed than K plus. Cesium plus is easily formed than Rb plus. Only one reason you can say metallic nature increases. Electropositivity increases. Electronegativity decreases. Simple. That means every point I'm telling leading to ease of removal of electron. That means ionization enthalpy decreases. Atomic size increases. Atomic size. So ease of formation of cation means ease of losing electron. Who is losing electron? Better way cesium. Why? It is having big size. It is having lower ionization enthalpy. It is having lower electronegativity. That means it is having higher electropositivity. So the same words I written. Ease of formation of cation increases down the group. Increase in atomic size, decrease in ionization enthalpy. I written two reasons here. And electronegativity. Decrease in ionization enthalpy and electronegativity. That is also reason. That means electropositivity increases. So because of this one, I can also write metallic nature increases down the group. Okay, that arrow mark represent down the group. And this represent down the group. So this is important. Okay, right. Now come to the next example. I take an alkaline earth metal, group 2 element. Group 2 element, I take a magnesium, especially 1s2, 2s2, 2p6, 3s2. These two valency electrons are written like a two dots. That is known as Lewis dot symbol. That is nothing but called as Lewis dot symbol. So if it loses these two electrons, it gets a neon electronic configuration, octet stability. So it is losing -2 electron. 1 electron lost means I'll get 1 positive charge. 2 electrons lost means I'll get 2 positive charges. So here magnesium 2 plus. See, stable electronic configuration. So okay, I told you group 1 metals are forming unipositive cations. The ease of formation of cation increases down the group. Cesium plus is the most easily formed cation. Because of its high metallic nature, high size, big size, lower ionization enthalpy, lower electronegativity, higher electropositivity. But what about the alkaline earth metals, group 2 metals? For group 2 metals, group 2, that means number 2, they form bivalent cations. Bivalent, two valencies, 2 positive charges. Univalent, 1 positive charge. Bivalent cations means beryllium, magnesium, written here. Beryllium, you can see the screen. Beryllium, magnesium, calcium, strontium, barium. The cation name does not change. Element name is directly carried to the cation. Beryllium 2 plus, Mg 2 plus, calcium 2 plus, Sr 2 plus, barium 2 plus. Okay, number. So they all form bivalent cations. Here, two things you have to tell me. One, compared to the group 1 metals, group 2 metals form more easy or less easy cations. That means the group 1, group 2 comparison, first one. Among the group 2 metals, the ease of formation increases or decreases down the. Here, two things you have to compare. So first come to the among the same group 2 metals. Down the group, as I discussed in the group 1 metals, here also, down the group, atomic size increasing, ionization enthalpy increasing, electropositivity increasing, electronegativity decreasing, metallic nature increasing. So ease of formation of cation increases. So Barium 2 plus is a big atom with a lower ionization enthalpy, higher electropositivity, easily lose 2 electrons. And barium 2 plus easily formed cation. So the same words I written here. I simply written alkaline earth metals here, bigger atomic size and lower ionization enthalpy. Two reasons other reasons you already know, familiar here. Metallic nature increases, electronegativity decreases, electropositivity increases. But come to the alkali metal comparison, alkali metals and alkaline earth metals. Across the period from left to right, metallic nature decreases. Atomic size decreases. Ionization enthalpy increases. Electronegativity increases, electropositivity decreases. That means alkali metals, group 1 are having the lower ionization enthalpies compared to the group 2. Group 1 are having the bigger atomic sizes compared to the group 2. Group 1 having the higher electropositive character compared to the group 2. And group 1 metals are best metals compared to the group 2. So group 1 metals form easily cations compared to the group 2. Formation of one charge cation is easy because group 1 metals tend to lose, group 1 metals only to lose 1 electron, but group 2 metals are going to lose 2 electrons. So alkali metals form cations easily in the respective periods. Okay, so that means lithium plus, Na plus, and K plus, and this is nothing but rubidium plus and cesium plus. Lithium plus is formed better than beryllium 2 plus, Na plus is better than Mg2 plus, K plus is better than calcium 2 plus, Rb plus is better than Sr2 plus, cesium plus is better than barium 2 plus. That's the reason I told you cesium is the most metallic element and the easiest atom to form cation. So easily forms a cation. All the sentences here I written down. So isoformation of cation increases down the group. Among these, alkali metal cations are easily formed the corresponding alkaline earth metal due to bigger atomic sizes and lower ionization enthalpies. I just got the reasons there. Okay. So far I explained 2 examples. I am discussing 9th point, formation of cations. Group 1 I completed. Group 2 I completed. Now I will come to the P block elements. S block elements I just completed. Group 1, group 2 are S block, belong to S block. 13, group 13, 14, 15, 16, 17, 18. 18 meant noble gas elements. I don't take that. They are not at all going to form any cations. I'm just discussing Lewis theory. Okay. So among these P block elements, I will take only one now. That means I am going to take aluminum, just to one example, because other elements are more complicated. They are having the variable valences. Only aluminum is having the fixed valence. That's why I will take aluminum as the example, my example. So group 13 forms a trivalent cation by losing 3 electrons. You see 1s2, 2s2, 2p6, 3s2, 3p1 is the electronic configuration. So 3 electrons is the outermost shell, Lewis dot symbol. This symbol is nothing but called Lewis dot symbol. All the electrons are removed. Now you will get the stable octet configuration. That is the aim, Lewis theory. Getting stable octet configuration. And aluminum 3 plus is there. Other elements are, why you not taking other elements? The group 13 is having some other metals also now. Even group 14 is having some metal, lead is there. I am not taking lead because lead is able to form 2 different cations. So at this point of time, it's a starting point. It is a little bit difficult. And exclusively, if I discuss group 14, then I will discuss energy pair effect and how oxidation states and everything. I will discuss that now. Okay. So right now, this is the example I'm taking. Okay. Now, after this, I'll come to the transition metals or D block elements. In the D block elements, I'm taking example number 4. I am taking all, that means I am taking considering all metals now. Okay. So far, S and P block elements I taken main group elements. By losing right number of electrons, valency electrons, they are getting stable octet configuration. That's correct. But come to the D block elements, group 11, copper, silver, gold, coinous metals and very expensive metals. Okay. Ornaments are made of these things, coins are made of these things. Earlier, kings are used to use gold for the making of coins. So, group 11, zinc, cadmium, mercury, group 12. In fact, zinc, cadmium, mercury are easy to explain. This is a little bit difficult to explain. Anyway, I will take silver now. Silver. Sir, why you are taking specifically silver? Here, like aluminum, that means I taken aluminum here. Aluminum is forming, can only form one ion, Al3+. It cannot form any other kind of ion. That silver also only form Az plus ion. Other ions are very rare. That's why I taken silver as an example. Copper can form copper plus is there, copper 2 plus is there. Gold can form Au plus is there, Au3 plus is there, like that. Variable valences are there. So more complicated, we'll meet these complications later. So much syllabus is there in the top class, okay? But I'm taking silver. So far, I given the examples which support the, during the formation of cation, they are all the examples so far I discussed. Group 1 metals, group 2 metals, and aluminum belonging to the group 13, all are following the Lewis rule. Lewis rule quite successful. Group 1, group 2, so many things, main black elements, it's quite successful. So losing electrons, forming cations and getting octet configuration, nearest noble gas configuration. Very good. But the first time by taking silver, I'm going to prove that silver comfortably without any difficulty forms Az plus, but Az plus is not having noble gas configuration. It is not having. So side by side, I'm discussing the failures of Lewis also. Everything I'm discussing, everything regarding the ionic bond and everything regarding the cations. And I very cleverly, that means choose these examples so that students at this level of, at this point of time should not get any confusion. Okay. Don't afraid of seeing the depth of the subject. It's very common. Okay. There is a big jump from the 10th class to 11th class. A really big jump. Okay. Now come here. This silver thing, 47. Atomic number 47, I wrote a complete electronic configuration so that you feel comfortable. The 1s2, 2s, first shell, second main shell, third main shell. And this is the fourth main shell, 4s2, 4p6, 4d10. After filling 4d10, electrons enters into the s orbital, 5s1. Okay. So you see 4d10, 5s1, be careful. Copper electronic configuration, I will write. Because you are very, you already know this copper electronic configuration, 3s2, 3p6, 3d10 and 4s1. Okay. Actually, the electronic configuration 3d9, 4s2. Actually, I clearly explained this one using the exchange energies and everything in the atomic structure. But 3d10, 4s1 is the real configuration due to completely filled d orbitals. Same copper, silver, gold are having the same electronic configuration. So this is the electronic configuration. You see, this is outermost electron, valency shell. This is silver losing this electron. One electron lost means one cation is given. So after losing this electron, come to this electronic configuration. What is this electronic configuration? 1s2, 2s2, 2p6, 3s2, 3p6, 3d10. Here 4s2, I just changed the color and I just boxed it now. Why? I will tell. This is the fourth main shell. Now this is the remaining electronic configuration. Remaining means after removing the 5s electron. You see, If this is only there, yes, Lewis rule is followed, octet configuration. But after removing the single electron, after removing the single electron, how many electrons you're having? 18 electrons, not 8 electrons in outermost shell. So why? That means why not? Yes. So sir, why not? I will remove 11 electrons to get a stable octet configuration. Like this is nothing but 4s2 4p6 is nothing but krypton electronic configuration. If I remove these all 11 electrons, I will get krypton configuration. I follow the Lewis octet theory. So if I remove 11 electrons, silver should get 11 positive charges. Anything with 11 positive charges is not at all possible. Anything more than 3 positive charges also very doubtful. Rarely you see 4 positive charges. 5 positive charges you don't see any at all. Okay. So if your argument is correct, I remove 11 electrons, I will get the krypton configuration, octet configuration. I follow Lewis' proposal. I have to get Az11 plus. That is not possible. Leave that one. Another possibility is there. Yes, another possibility. Sir, here 5s1 is there, na? 5p also there, na? Yes, 5s is there, 5p there. Here 1 electron, here 6 electrons. 5p6, total 7 electrons. I take 7 electrons from some other species. 7 electrons will be taken from some other species. Then its electronic configuration becomes what is that 5s2 5p6, that immediately becomes xenon electronic configuration. Again, I'm following the Lewis theory. Again, I'm getting the stable octet configuration. So if I lose this electron, I will get the krypton, and a silver gets 11 positive charges. Alternatively, if I get 7 electrons, 1 electron is already there. If I get 7 electrons from other source, I will get 5s2 5p6 of xenon electronic configuration. That also stable electronic configuration. If I get 7 electrons, Az is 7 negative charges. Ion formation. The first one is silver is metal. It doesn't like to take electron. Okay. The second one is anything 7 positive charges. That is a joke. Okay. So no ion exists with 7 negative charges or 11 positive charges. So Az 11 positive charges is not possible. Az 7 negative charges is also not possible. When compared to these two, this is more reasonable, even though I am not getting stable octet configuration as Lewis said. So this is a failure of Lewis theory. Octet theory failed. Even though Az plus is not having octet configuration, it is stable. What Lewis is telling? Visweswara, something should have octet configuration to be stable. But Az plus is still stable without octet configuration. And more importantly, look at this one. This having 18 electrons in outer shell is called pseudo inert gas configuration. Pseudo noble gas configuration. My word, pseudo. What is the meaning of pseudo? Pseudo means it is not actually there, but we feel it is there. That is pseudo. I definitely understand. And a beautiful Telugu word is also there for pseudo. Okay. Mithya. Mithya. That means which is not there. We feel that is there. That is pseudo. Inert gas configuration is not there, but we are feeling that is there because of completely filled shells. All shells are completely filled. Definitely stable, even though it is not inert gas configuration direct. That's why it is inert gas is now named as noble gas form. I'm sorry, I'm repeatedly using inert gas, but while I was studying, that is the name I used to learn. So here also I written here now pseudo noble gas configuration. Here itself I written that. D block elements form cations with pseudo noble gas configuration. Pseudo-noble gas configuration friends having 18 electrons in the outermost shell. Cation is having 18 electrons in outermost shell. So the entire discussion, what I so far told you, written here now, to get the everything you can read it now. I don't want to waste my time here because I already explained here. So presence of 8 electrons is relatively favorable than Az 11 positive charges, Az 7 negative charges. Okay. So what about copper, sir? Copper also forms copper plus mana. Same, it is having pseudo noble gas configuration. Au also forms Au plus mana. But those examples, I will tell that one definitely. Here you see, I'm writing copper plus configuration with this 18 electrons. Az plus I just explained. Au plus is also having 18 electrons. But copper, gold are having the tendency to form other cations also. That's why I have not taken that example, because so too much discussion is also too much depth at the starting point, also difficult for you now. So we'll anyway get all those things after completion of D block elements in 12th class, right? I'm okay with this. Now this group 12 elements are relatively very easy now. These are very easy because they only form one cation, Zn 2 plus, cadmium 2 plus, mercury 2 plus, but mercury is having tendency to form different cations. Okay. So zinc is very easy to understand. It only forms one cation, Zn 2 plus. So I taken zinc as an example. So I think like that. That means before taking any class, before coming to one conclusion, in so many directions, I think, and I question myself in many ways. And once I satisfy, then only I go to that point now. So I'm not taking mercury. I'm taking zinc because mercury is having very good balance. See? So this electronic configuration, I just not written completely. Neon means 1s2, 2s2, 2p6. Instead of this one, I written neon. This is electronic configuration reachable. That means every student in this classroom know that I written this electronic configuration in atomic structure. It loses these 2 electrons simply, that's all. Losing these 2 electrons means it is getting pseudo-noble gas configuration. That is a kind of stability. Okay, it is violation of Lewis theory, definitely. Lewis failed. Lewis theory is the basic theory, Nana. And I am telling every theory, that means generally students think that after Lewis theory, I will discuss Linus Pauling theory. After that, I will discuss molecular orbital theory. Never think that Linus Pauling is better than Lewis. Molecular orbital theory is better than Linus Pauling. Not like that. I discuss those theories in that order because those in the order of their difficulty level, not in the order of their superiority level. Lewis theory is easy one. Never underestimate Lewis theory. Lewis theory is the easy one and simplest one. Explains so many things. Okay. Linus Pauling is more complicated than Lewis, and molecular orbital theory is very complicated. Only diatomic, homonuclear diatomic molecules is there for the 11th and 12th class students. Later on, that becomes very, very difficult. Okay. That is all, not at all there. Only in the order of difficulty I discuss like that, not in the order of superiority. And one very important thing you have to understand, every theory is having some drawbacks and some greatness. Okay, every theory, whatever it is, even molecular orbital theory, whatever the theory you propose, definitely it will have some drawback. It will have some greatness also. Every human being also will have drawback. And some plus points, some minus points, good points, bad points. Nobody is no theory, nobody, nothing, no construction, no device is 100% perfect. Expecting 100% perfection from anybody leaves you in a miserable condition. Okay. I'm telling, expecting 100% perfection from anything, any device, anybody, any human being, any construction. You look at the wall of your house. Oh, this fellow is not did very well. You feel miserable. that is a miserable condition. Don't expect 100% perfection from anything. It is not there. It is not there. So don't underestimate Lewis theory because it's simple. It is really simple. And now this is even, it is violating Jadan 2 plus. According to Louis telling Mrs. Rao, Louis is telling Mrs. Rao, anything, any cation is stable only if it is having the stable electronic configuration. But I am telling sir, Jadan 2 plus is there, it is quite stable there. It is not having octet electronic configuration. Even though it is not having octet electronic configuration, it is stable. Jadan 2 plus is stable. So here again, I return inert gas. So that inert gas is went into my blood veins. So I will have to change myself. So pseudo noble gas configuration relatively favorable to other possibilities. That's what I mean. Now. So in this example number 4, this example number 4, I completed D block elements. D block elements I completed. Now, in the example number 5, listen by what's careful. Now I'm going to a little complication. D block elements, I wisely chose very particular things because they do not form any variable valences. But now, what if D block element is having different cations, variable valences? Iron shows variable valency. Fe2 plus is there, Fe3 plus is there. So transition metals generally form different ions. Okay, so many different possibilities are there. Copper plus, copper 2 plus, cobalt 2 plus, cobalt 3 plus, nickel 2 plus, nickel 3 plus, like that. Okay. In that case, at least one example you have to understand. In that case, what happens? Are you going to get pseudo noble gas configuration, or you don't even get that known pseudo noble gas configuration? We'll see. Iron electronic configuration. This is iron electronic configuration 3s2, 3p6, 3d6, 4s2. This is the outermost. Fe2 plus spin, these electrons are removed. You see this electronic configuration. It is not octet configuration. It is not even pseudo octet configuration. That means pseudo noble gas configuration. Why I am giving this example? I'm afraid maybe if I don't give this example, maybe you record a wrong thing in our mind. Ions with the noble gas, either noble gas configuration or pseudo noble gas configuration, only stable. No. That conditions are not at all necessary. Okay, that means octet configuration. Okay, pseudo octet configuration or noble gas configuration, pseudo noble gas configuration, that is also okay. But ions even exist without those things also. Fe2 plus is quite stable. It is not having any noble gas or pseudo noble gas configuration. Fe3 plus is also stable. It is also not having 8 electrons or 18 electrons. But I can say Fe3 plus is a little more stable than Fe2 plus because it is having off-filled orbitals. See, clearly not following octet rule. So that is the reason. Now I'm coming to that. If you take copper 2 plus also, same thing happen, but copper 2 plus I don't want to discuss right now. Now come to the lanthanide elements now. Those are also metals now. So all kinds of metals forming different ions. Okay, I'm telling that one. This is the most important discussion now. And coming to the lanthanide elements now. Lanthanide elements means lanthanum is a D block element, remember. Cerium to lutetium, 4F series elements. Cerium to lutetium. Atomic number of cerium is 58, lutetium atomic number 70. So lanthanum also behave like these elements. That's why we collectively call these 15 elements as lanthanide elements. Remember, these are 4F series F block elements. This is simply D block element. No F orbital electron is there. D block element. All forms a common +3 ion now. +3 ion. All form a common +3 ion. Variable valences are there, but +3 is most common. That's why I written the electronic configuration. It is so helpful while solving the periodic table problems also. It is helpful to you. And keep the periodic table with you, electronic configurations with you while solving the problems. It's no problem. You just go through the electronic configurations every time while solving the problem. You feel more comfortable. Lanthanum xenon up to xenon is there, Nana. I written the remaining electronic configuration. I told you now 4F is having no electron, 5D1 and 6S2 D block element. Lanthanum 3 plus means all these electrons are lost. It gets, once all these electrons are lost, it gets xenon electronic configuration. Octet rule is followed. Quite stable lanthanum 3 plus. Octet rule is followed. But come to the gadolinium. Why I taken gadolinium? It's very, very important. That means it is 4F series, F block element. Gadolinium is in between the cerium and lutetium. Its atomic number 64. I written F block element. And xenon atomic number 54. That means up to xenon 54 electrons I filled. I'm not writing. If I write this electronic configuration, it comes across this entire page. Not necessary. So why I taken gadolinium? Gadolinium is the most favorite for the paper setters because it is having off-filled F orbitals. Off-filled F orbitals. Okay, number. Off-filled F orbitals means that is a special element. Okay. Now gadolinium forms 3 plus ion. So I told you, lanthanide elements are most commonly form 3 positive charges ion. These d electrons are removed. You say xenon 4f7. It is not following octet rule. It is not following pseudo noble gas configuration. It is not following any rule. But I feel it is quite stable because this ion is having off-filled F orbitals here. Octet rule is not followed, but off-filled F orbitals give stability. What about the last element, lutetium? I not written here. You try that one. Lutetium 71, xenon 54, 4F14, 5D1, 6S2. This is the electronic configuration. This is the electronic configuration now. Okay, now? And it loses these 3 electrons. It is having 4F14, completely filled F orbitals. Lutetium 3 plus is stable. Yesterday, in the period table, I told about the element having atomic number 71 forms 3 positive charges. And this is the reason. Yesterday also I given this one. And okay, right now. So I can accommodate that example also, so that I will accommodate that one also now. That one also. It doesn't take much time. No? 1 second here. After completion of lanthanide elements and lutetium also, I completed here. Lutetium 3 plus is stable because of the completely filled 4F orbitals. Now come to actinides. Actinides also form plus 3 ion. So you will get more detailed in the 12th class. But right now, you have to understand some basic thing now. Actinium is D block element. You see this electronic configuration. 5 of our electron is not at all there. It is the D block element. Okay. So actinium is a D block element and it is losing 3 electrons. It gets noble gas configuration. Actinium 3 plus is having octet configuration. Nice, stable. Now, from thorium to lawrencium, I will take a curium. I am taking curium. Why, sir? Why you are preferring curium? Curium is having off-filled F orbitals, 5 F orbitals. Curium 3 plus Cm. Curium means Cm. Okay. 96. Radon, that means actinium electronic configuration also up to radon 86, 3 more electrons here. Here 96 is there, up to 86 radon and other 10 electrons here. And in formation of 3 positive ion, that means trivalent cation, it loses these electrons. It is not following any pseudo noble gas configuration, but it is stable due to the presence of of Loctet rule is not followed, but off-filled orbitals give stability. I'll write here. So the electronic configuration of Lawrencium also I will write. Then you feel last element. That is the last element. So that is this is nothing but Lawrencium is Lw. Its atomic number is 103. This is radon up to 86. What is the specialty? Completely filled F orbitals are there, and its electronic configuration is 6d1, 6d1 and 7s2. It is losing 3 electrons. You will get a Lawrencium. That means I'm a little bit sorry, Nana, that I mistaken here. So Lawrencium, that is L or Nana. I'm sorry for that. So Lawrencium 3 plus, and this is nothing but 3 electrons. So what is the electronic configuration here? 86, 5 of 14. Here also definitely octet rule is not followed. That means what I'm telling, even though octet rules are not followed, so many are there not? So many ions are possible, even though they don't follow octet rule. Now here, stable. Why it is stable? Having completely filled 5f orbitals. So these are really helpful. The examples so far I given are real examples, are really helpful examples. You will get if you get out of the fear of Lambda elements, transition elements, D block elements. Okay, no need to get fear about those things. Nana. All are metals. All are metals. Nana. All are metals, but definitely they form cations, and I given the formation of cations. Nana. So cation formation I given here. I explained every bit of that one. Nana. Later on, while I discuss specially, for example, in group 13, boron, aluminum, gallium, indium, thallium. Thallium is forming +1, +3 ions, variable oxidation state, that is P block element. Thallium plus is quite stable compared to the thallium 3 plus. What is the reason? The reasons are not octet configuration, not those reasons. Okay. You have to pair effect. Some more subject is there, oxidation number, those things. So while I will discuss the group 13, I will discuss the complications of that variable oxidation state, like group 14, carbon, silicon, germanium, tin, and lead. Lead is able to form +2 and +4 ions. +2 is more stable compared to the +4, like that. So this is all from the formation of cations. Tomorrow I will take up formation of anions. Formation of anions is not that much complicated like cations. Most of the examples follow octet rule because very small number of non-metals are there in periodic table. Right side of the periodic table, fluorine is the best non-metal. So they generally follow octet rule. And once you got the formation of anions, you already know how to define ionic bond, and that is completion of ionic bond. So tomorrow I'm going to come